My name is Yue Kuang, and the topic of my project is application of reinforcement learning in text-based games. Natural language processing is a well-established field with the ultimate goal to read, decipher, understand, and make sense of the human languages by machines, taking certain tasks off the humans and allowing for machine to handle them instead. Common real-world examples of such tasks are online chatbots, text summarizers, auto-generated keyword tabs, and so on. While reinforcement learning approaches lead to significant achievements in a variety of areas, natural language tasks remained mostly unaffected due to the compositional and combinatorial nature that makes them notoriously hard to optimize. Researchers find that text-based games can be a good testbed for research at the intersection of RL and NLP. Text-based games are complex interactive simulations that use natural language to describe the state of the world, to accept actions of the player, and to report subsequent changes in the environment. The player works together, which are seldom specified explicitly and must be discovered through exploration. The observation and action spaces in text games are both combinatorial and compositional, and players must contend with partial observability, since descriptive text does not communicate complete and clear information about the underlying game state. The project investigates several deep reinforcement learning models proposed in recent years that can be applied to solve text-based games. We will also introduce Microsoft Text Word Framework, with which a competition was designed to specifically foster research at the intersection of reinforcement learning and natural language processing. Based on the model's performance on the framework, we can see a promising future of the application of deep RL in the field. Limitations and future directions will also be discussed. Now let's go through the project in detail. In 2015, Narasimhan proposed LSTM DQM model, which consists of two main parts. The representation generator at the bottom takes as input a stream of words observed in state S and produces a vector representation VS, which is fed into the action scorer at the top to produce scores for all actions and argument objects. The model utilizes the representational power of the hidden state of long short-term memory to learn a queue function. In 2016, He et al. Proposed Deep Reinforcement Relevance Network, DRRN. It consists of a pair of deep neural networks, one for the state text embedding and the other for action text embeddings, which are then combined in a pairwise interaction function to compute the Q values. The motivation behind the design is that the text to describe states and actions could be very different in nature. For example, a state text could be long, containing sentences with complex linguistic structure, whereas an action text could be very concise or just a verb phrase. Therefore, it is desirable to use two networks with different structures to handle state or action texts, respectively. A summary of the full learning algorithm is shown on the right. As we have introduced, during forward activation, Q function is estimated in two steps. First, map both state and action to their embedding vectors using the corresponding deep neural networks. Second, approximate Q value using an interaction function, such as the inner product of the embedding vectors. At the end of each iteration, we can see that backpropagation is applied to learn how to pair the text strings from the reward signals in an end-to-end manner. The representation vectors for the state text and the action text are automatically learned to be aligned with each other in the text embedding space from the reward signals. In 2018, Microsoft Text Word Framework is established. It is an open-source extensible engine that both generates and simulates text games. In the framework, an agent can learn a specific skill that it can then prove to generalize to an environment. The first text word problems, a language and reinforcement learning challenge, was a competition designed to specifically foster research at the field with agents that generalize across a whole family of similar TPGs. The competition is based on TPGs from the text word framework that all share a similar theme, namely cooking in a modern house environment. The agent is placed in a random initial room and is asked to find the cookbook, read it, and then prepare the specified recipe. The recipe contains several ingredients that need to be collected in the rooms and directions, which need to be executed to prepare the meal. Throughout the game, there are multiple obstacles to overcome, including navigating through different connected rooms, dealing with closed doors and objects, finding the right tools, as well as collecting the right ingredients. With the improvement in testbed for reinforcement learning agents, at the same year, researchers pointed out the shortcomings of the two models we introduced before, that is LSTM-DQN and DRRN. Firstly, they are not conditioned on previous observations, and so are at a disadvantage when dealing with complex, partially observable games. Additionally, neither of these approaches prune the action space, and so end up wasting trails exploring state action pairs that are likely to have low Q values, likely leading to slower convergence times for combinatorially large action spaces that arises from games with different objects and the nature of natural language. In 2020, Adolphs and Hoffman proposed the deep shift. The model architecture consists of 4 building blocks. First, the context encoding block. The input to the context encoding are the 8 text-based features, including the past context and its previous division. Each of them is a sequence of words embedded using a trainable 100-dimensional word embedding. Next, the commands encoding block. At every timestamp, the model has a set with varying lengths of different possible commands to choose from. Each command is embedded in the same embedding matrix as the context encoding. Next is the value computation block. An advantage actor-critic approach is utilized to train the agent. This approach requires a critic function that determines the value of the current state, which is a multi-layer perception with a single hidden layer and value activations. And the last one, scoring and command selection block. For each possible command, a scalar score is obtained by feeding the concatenation of the encoded context and the encoded command into the neural network. We can get a score vector that ranks the k possible commands as output. A softmax function can then be applied to turn it into a categorical distribution, based on which the final command can be sampled. In a word, the researchers designed an architecture that uses different parts of the context to rank a set of commands that is trained within an actor-critic framework. Through recurrency over timestamps, a model that is aware of the past context and its previous decisions is constructed. On the other hand, one of the major challenges in TPGs is the construction of reasonable commands in any given situation. Since the size of the search space is vast, brute force learning approaches are infeasible, and RL optimization is extremely difficult. To solve this problem, researchers effectively reduce the size of the action space by combining multiple actions to high-level actions. Moreover, a helper model that is specialized in predicting the remaining cooking actions to complete the recipe is trained. Moreover, a task-specified module is also incorporated. It predicts the missing steps to complete the task and is trained on a dataset based on BGB recipes augmented with a list of the most common food items found in Freebase to make it resilient to unseen recipes and ingredients. Now on the screen, we can see a comparison of all the models we have introduced on the text word challenge games. The metric is points per game related to total achievable points throughout the training of 3 epochs with 10 different random seeds. Each shown point is an average over the past 80 games. The plot on the left demonstrates DRRN and LSTM DQN performances compared with 2 baseline models. We can observe that both models significantly outperform their random counterparts over the course of the training, but are not able to learn to solve the games to a sufficient degree. The big scoring difference between the 2 random agents underlines the importance of effective action-space production. The table on the right shows the quantitative results of different models on the unseen validation set, as well as the final test set of Microsoft's text word challenge. As expected, the Deep Chef generalizes best to the unseen games. Throughout the project, we know that text-based games is an emerging and promising field at the intersection of reinforcement learning and natural language processing. There are several main challenges including large action space, efficiency of RL optimization algorithm, and the ability to generalize to unseen games. Researchers have been facing the challenges, making progress in developing new models, as well as improving benchmarks to foster the research environment. However, there also exist limitations. Natural language processing related models rely heavily on human annotated data, which involves an expensive, time-consuming, and error-prone process. Moreover, most of the models are still offline supervised learning methods, which can be lengthy and fail to capture trending requests. In the future, researchers may look into solutions for models' reliance on data annotation. It is also worthy to exploring online learning methods, which can improve the model's adaptiveness to changes in data distribution. Moreover, the combination of neural net models and reinforcement learning could become the next best approach in sequential decision-making and parsing. The reason is that, on one hand, neural models can be very effective with other natural language problems, such as machine translation. And on the other hand, reinforcement learning methods would allow the agent to keep adapting to changes in a natural language. Since the very nature of this algorithm to learn through interaction, and this feature allows reinforcement learning agents to constantly adapt to changes in their environment. Here are the references. And that's the end of my presentation. Thanks for your time and attention.